speaker is Husain. He's a committer for FoundationDB. He works for Snowflake. And today he's going to be talking in depth about how encryption is implemented in FoundationDB. Atta, take it away.
Thank you. Hi everyone, my name is Husain. Little longer name, please feel to call me Atta. I have been working at Snowflake for roughly 3.5 years, and this talk is more in depth about encryption. And thanks Himank and Arvind for introducing FoundationDB. I'm going to do that again. The purpose here is take you to the journey what Snowflake did for implementing native encryption, because that was one of the gaps we found when we started using FoundationDB, and I can see Jingyu in the group, so we have been tracking with him a lot. So the primary use case was as Himank was mentioning, people use FoundationDB in Snowflake actually use FoundationDB where the data is sensitive, and when you're using it, either you have a choice of implementing encryption at the application level and then pushing the data down. So we found that the best thing to do was to have a database support native encryption, and which is a very common practice for other industry standard databases. So the goal here is to kind of take you to the journey, give details about what we did, but also kind of give some details about why we did what we did and how we reached there. And then maybe kind of strike this brainstorming session wherein if things can be improved, if how we can make easy integration for others to use it, or what we see to be gaps that could be filled later on. And that will be a very glimpse of what the future will look like, because I think I have only 30 minutes. I'll try to kind of wrap it up and see how far I can go. So starting with what were the goals when we are thinking of what the encryption at rest should look like. So first is we were kind of laser focused that we want to just take data at rest part of it and not the memory encryption. So everything that gets stored persistently on databases should be encrypted. That is the goal that we started with. Second is when we talk about encryption, there has to be silos. One way to do that is use a single encryption key, and then you kind of encrypt all the data that you write. And that would be I would say not easy, but one of the ways to do that. So we didn't want to go that route, and we want to make sure that we have some domains, some isolation domains wherein you can bound them and be closer to the NIST standards of making sure that the creator, if an encryption key is lost, is limited. Limited both from the tenant side, both from the timing side. So we first defined what a domain would be. And I'll go more into that, but what we did was we created these logical silos, and our encryptions is bounded by those logical silos. In following slide, I'll say what those logical silos were. Most importantly, we wanted to have an easy integration story. So one other thing which is implicit here is we did not implement vault in FDB. FDB doesn't act like a vault. What FDB does is it only provides the semantics of encryption, but it assumes that there is an external input which says what encryption keys to use, and it maintains all the properties of generating, storing, maintaining the life cycle of it. FDB gets it as a blob and start using it. So we wanted the integration to be very, very easy. Any organization should be able to plug in the wall of their choice and then start using with it. The semantics wise, we tried to be closer to what NIST recommendation is. The ciphers has to be rotated, the life cycles has to be limited. And then CMK, the full form is customer managed support, which is not existing today, but that is always in our mind to say how we can scope wherein a customer is a part of an encryption story and they have a right to revoke whenever they want to revoke a particular silo or logical partition. Again, please feel free to stop me at any point. I will try to go fast, and I naturally speak faster, so if I'm doing too fast, please slow me down. Now, I talked about the domain. So what we did was there was another work wherein the tenancy or multi-tenancy was getting more implicit as a part of FoundationDB. So FoundationDB defined a concept of a tenant, and a tenant is nothing but a logical partition. Given FDB is a key range-based database, you can define a key range, and that key range could be a logical entity from a customer side. It could be anything what customer defines. So we latched onto that concept, and then it was now being physically defined as a tenant. So you have a tenant, we can have a identifier as a tenant ID, and our encryption kind of hinges to that tenant. So every tenant is considered as a different silo, and you are supposed to actually have, if you want to, the recommendation is every silo would have a distinct encryption key that you can use. You can use everything as a single silo, that is fine. Like one domain for all is acceptable, but if you want to go more granular, it is possible to have multiple domains and each domain ties one-to-one map to a tenant in FDB. And there is a flow where you can create a tenant, and that's how a tenant becomes a recognized entity within an FDB. Another property which we liked, and that was kind of important for us, was the transactions in FDB, as Himink was mentioning, they may contain multiple mutations, but when you go into a tenant mode, the boundary is limited to a single tenant. So one transaction would have multiple tenants, but they will all be part of a single, or multiple mutations, but they will all be part of a single tenant. And that property is kind of enforced by having these discrete transaction domains, wherein one transaction will be limited to a tenant. And for some reason, for our use cases, that was a very good fit that we latched onto. Now, starting with like how do we configure and how do we use, and then from there I'll kind of go a layer deep into how it is implemented. Like given the encryption is a very fundamental feature. So we first thought about the basic principles of how a user will configure it. Will be possible to toggle it, like, it's possible that you start with a database state A, then you go to the encrypted state, then you go back to unencrypted state. So we made some hard decisions, and, like we found that to be more reasonable and also kind of, more convincing for us that it seems strict, but following that makes life a little easier. So one is we were very thoughtful in terms of making that the configuration should be very limited. So the whole encryption is controlled by a single database config. Again, database config lives in the FDB itself. As a part of a database creation, you supply that I want to enable encryption. It's called as encryption mode. And you toggle it on, and that property is sticky. Like you cannot change it once it has been set. So one of the limitations here is if you have an existing database, you cannot go and flip on encryption on that database. It only gets applied to new database that gets created, or whenever you create a new database. So this was definitely something that, restricting, but we thought that it is easy to actually just kind of have encryption set once, you cannot reset it, and from there the state of the database is always deterministic. Now, coming back to the modes, today we have two modes, wherein you can imagine that you want a single domain for the cluster for some use case, plus you want your flexibility to define multiple domains. So we have one strategy which you can set called as a cluster away. Again, sticky, you cannot change it. And what it means is your full cluster would be a single domain, and everything, all the data would be encrypted by one set of encryption keys that you supply or your vault is supplied. The second one is a domain aware. And one of the classic examples is like, in your case, if you have multiple tenants and they wanted to have better segregation, what you will do is you will go into this mode, which allows every tenant to have a disjoint set of encryption keys. So if for some reason one domain fails, it doesn't impact, or the critical impact is much limited. Now, given we have now bonding the tenant mode and encryption mode, there needs to be some rules. So the rule was, if you go to domain aware, then you need to have a tenant required, which is another configuration wherein what it forces is once this flag is set, then every transaction you do would have a tenant ID associated with it. There are only very few transactions you can do, like for example, clear ranges, you can do it across, the full database, but then that we handle internally because clear ranges is only a multi-key transaction. Otherwise, everyone is a single key transaction. So for the clear ranges, a special case that is handled, and I'll talk about it. But every transaction needs to be tagged. If you are in a tenant mode, then you cannot say, I don't specify a tenant, but I want to do this transaction, that will fail. So, and that goes very well, a one-to-one map with our domain aware strategy, wherein if you set domain aware, then your tenant mode has to be tenant aware. You cannot actually just, mismatch them. Cluster aware, cluster scope, you can do whatever you want because it doesn't tie with tenant. So you want to have a tenant as a part of transaction. You don't want to have it, that both will work fine. So this is from configuration part of view, this would only like you set this few modes, and then once you set it, you cannot unset it. And that is all you need from database configuration to support native encryption. Now, these are more of a guidelines, and this was more from what we learned through the journey of what a vault could be and what it should in a recommended way provide. So what an ideal vault, or in a way, our opinion, what ideal vault would provide is it should provide a key wrap and wrap functionality because, as a vault, the standard for maintaining encryption keys even higher than your data store where your data is being stored, because one key has a much bigger impact, and if that gets leaked, more of your data gets leaked. So you need to have a very strong strategy wherein your vault is able to wrap and unwrap encryption keys, and that it will do on the basis of whether you're writing or reading the keys from the vaults. It has to have a very good persistence story. You cannot actually lose encryption keys, because lose encryption keys is technically data loss. Once that key is lost, you cannot read it. So the persistence is like, it cannot be taken for granted. It needs to be as reliable as possible. It needs to maintain the life cycle. And the life cycle is this was mostly to be aligned with the accepted NIST standards, wherein you need to create encryption key for performance reasons. Maybe you create it in a lazy way, because you will not be creating encryption keys that often. Second is you need to rotate it. So like FoundationDB encryption do support a rotation or a life time to live for a key, and your vault can support that rotation by periodically having generating the newer keys, so the data can actually use the newer key when it's get written. However, the older keys can still live, and they can be serving the data which is already persisted there. You can have a background cleaner or garbage collector to just collect the encryption key so that it doesn't get unbounded. From our point of view, just for the integration, it needs to at least support two types of lookup. One is for the writes, what we do is we care about what is the latest generation for that particular domain or a cluster. So it needs a fast lookup ability of say, I just give a tenant ID, just give me the latest or the current encryption key. Second one is I can look up the key to store or read any of the data that is written in the past. And for there, what I will do is I'll give you a generation ID or a unique ID for the key, and you give me back that key. That is like a lookup one. So your vault needs to at least have these two APIs, and that I'll explain why it is needed, because that's what our integration to the FDB hinges on. Lastly, in memory caching, because given encryption keys, the lookup is one of the calls which is the FDB has to make to a process which is not FDB. So you will be incurring RPC, and that will be coming as a part of your inline. It could become as a part of your commit or a read. So it is latency sensitive. So it is better that your vault has some in-memory caching so that this calls are as cheap as possible. Now, once we have, now coming back, switching gears to the FDB part. FDB has a network layer, like I'm pretty sure people who have used it, has FDB implements a proto layer. It has its own definition of what the endpoint is. What we saw is there was a gap wherein now what FDB need to do is FDB needs to talk to an entity which is not FDB. So you cannot use the same protocol mechanism which has been used by FDB to FDB process communication. So we had to implement this whole tier of the networking, which will allow FDB to reach out to a vault and then do what it needs to do. So there was this consideration of how would you configure it. So to make life easier, we again try to limit the configuration, and everything is governed by foundationdb.com. So there are a few entries in foundationdb.com, and that's what governs how your communication between FDB and KMS stands for Key Management Service, a generic word, would work. Now, on the startup, what you need to do is you need to discover where your KMS are. That's like problem number 0. So what we implemented today is we support a user to supply a file, a local file system file, and that has a URLs to where your KMS lives. And that is we call it a file-based discovery. It's easily extensible. Like, we ourselves have plans to actually extend it. So you can have a well-known endpoint that you can go to. You can have a file strategy. You can actually directly have any compatible APIs to KMS, which will be, you can configure as part of database creation and you can reach to. But for now, what is implemented in main and also the Snowflake branch of FDB is you supply this file, it passes the file on the startup, and it knows where to reach out to. It has this, given we are talking to vault and everything has to be super secure, because the communication is the ciphers, the encryption keys itself. So we has this inbuilt authorization mechanism, and that is based on the tokens. So what you supply as a part of a configuration is you supply, where your tokens or what your tokens that you every request will pass, which Vault has to agree upon that I know this FDB host, and I authorize it to read or write encryption keys. So it's a token based. You can specify as many tokens as you want, and the code is well documented. It says what format the token needs to be. So there is an inbuilt authorization built between communication. And lastly, we wanted this model to be a plug-in model. Like what we implemented is an HTTP REST protocol of communication, but somebody may want some other protocol, a gRPC or SOAP or whatever. So in C++ world is basically a generalized class and a specialized class, wherein we have implemented a REST-based specialization. But if we want to have another specialization, it could be easily done. It is all controlled by configuration in FDB. So once you configure it, you can plug in your favorite model, and that integration will just work. For performance reasons and for unit testing, we do have, I would say, a kind of a pass-through, wherein we implemented a perf connector, where it doesn't go to anyone else. It kind of terminates the calls right there. So the process itself just kind of do a jump of a function call, and you can implement your lookups for encryption keys, and that we use for testing how or what is the penalty for encryption without incurring any of the RPC latencies which goes outside of DB. So we call it as a perf connector, but basically we use it for all benchmarking of how expensive the native encryption is. And the reason being, it is always on. You want it to be a very minimal penalty, because you will be every call needs to be using it for reads and writes. So that was for the communication part. Continuing that journey, like what we did was we talked only about how the configuration will work through. Now there is another aspect of how you will establish a connection. Will you maintain a connection pooling? What will the protocol of communication between the FDB and KMS? So similar to the network proto, which is a part of FDB, what we did was we implemented this REST client, and here there are pointers in the codes which will probably anybody who wants to go and look at it. So the REST client is a full-fledged class. What it does is it maintains this semantics of connection establishment, connection pooling, and the idea is you can maintain n long-lasting connections, and you can bound them. So if you want not to be overwhelmed and you have a limit on number of open connections, you can control them. So if there are more number of requests, it will still allow or make an ad hoc connection, but will not pool it. So, and the connection pooling has a time to live as a parameter. You can keep that connection as long as you want, or you can bound them and say, by the way, I want to kind of terminate it after a while. So it's small, but what it helps is it helps with the runaway connections, which will be open for a long, and then it can actually penalize your services in the production. So inbuilt check wherein you can limit the number of connections as well as time to live for those connections. The protocol supports all, I would say, common or significant REST functions like get, head, put, post, delete, trace. Mostly what we do is we have using post for all of our communications, but if anybody wants to use any other REST implementation, that is already there. The connection supports it. Lastly, what we found was the connection between FDB and KMS is one of the most critical connections, because if that connection is down, the cluster availability is now tied to it. And the reason being is if your connection, if your commit times out, and the way FDB works is it will be like, if one of the commit on a commit proxy kind of times out, it brings the cluster down. And when your recovery is happening, again, you would need an encryption key to even read your metadata. So the recovery, the very first thing it will do is it needs to read some encryption key so it can actually recover the cluster back. So keeping that, the high availability part of this connection into our mind, what we did was we support this retry with exponential backoff to have an outage-like scenario wherein if your KMS is down for some reason, your cluster still would be just kind of trying to reach out to it. More to that, what we did was we also allow, and that's kind of the last bullet of the KMS selection, wherein you can supply multiple KMS ports or URLs, and the system is intelligent enough to sort them. So it will track the health of each URL in terms of what the latency of the response is, whether I'm seeing a lot of connection timeouts or connection fail. And also because, the request or response are versioned. So you can keep your vault a different version as your FDB. It is possible that, you are talking about it's a cross communication where the vault version is not even supported at FDB, and you could get a response which is say, I don't even know how to pass this response. So based on those failures, you can, the system sorts which ports or which URLs are the best one to reach out to, and it will, in a fashion, just try to go forever loop if a connection is broken. So, and the idea here is most of it was kind of learned through the experience when, we found using first the simulation was our tool in our production system. We found that to be broken, and, it was a journey wherein we kind of just kept tightening those screws to see, how we can improve the reliability on that. And again, the journey is not over, but, we'll just keep trying to improve on this. Now, the specific connector that we implemented, we call it as a REST KMS connector. It is REST-based. The request and response are JSON objects. And the JSON, it's both forward, backward compatible. The request and response by themselves are version. So you can just keep on increasing the version on either side. And you can read cross version as well if your code is compatible to do that. And we found that to be very easy for upgrades because, if the clusters have different versions, you can actually have no outage in some ways. Now, the second part of the journey, once we, so we started with the wall. Now we know how to connect, the FDB connects with the wall. How we do the encryption key management. So now encryption key management is important because, your vault is an expensive resource to reach out to. So FDB needs to have a way of how to represent the cipher that it has read, how to maintain the lifecycle of the cipher, and how other FDB processes, and I'll talk more about why other FDB processes needs to do it, because how other FDB processes will consume this information. So given this is, in FDB, if we call it as a role, and role is nothing but a process, or rather a responsibility for that process, what it will be doing. So we found that, given the key management is that important, we added a specific role which acts as a center or a basic router for all the encryption operations. We call it as an encryption key proxy. And in the detail wise, it is implemented as a singleton. So that singleton gets recruited as the very first thing during the FDB recovery startup. That singleton life is not tied to any, not tied to a sub-transaction system. For example, if a master dies or any of the commit proxies dies, your system will recover. But we don't want the singleton to recover because the singleton also implements the caching, and your encryption key vault caches will be dying away. So again, this thought being put so that we make this process as available as possible. We make sure that the data that it caches is also not lost just because any other system or any other process is actually dying. So that is why the singleton is what it is, and then why it is not being tied to a sub-transaction system, and why recovery doesn't always recruit again and again. From endpoint wise, it implements two important endpoints. One, it knows how to reach out to KMS, that is an outbound. Inbound is other FDB processes knows how to reach out to encryption key proxy, and we'll talk about why other FDB process needs to reach out to it. But for now, it implements these two endpoints. Again, it is a extensible interface. Anybody can add one more interface to, or rather one more endpoint, and with other functionalities. The reason I say extended interface is because we started our journey with encryption key REST use case. We internally call it as EAR. But then again, we found that, it was because we have now an outbound way to reach out and fetch information, we now also use it for fetching the blob credentials. And that is, if you're following FoundationDB, there is an addition wherein we added a blob store support, which can be used for storing large files for like backups. And those backups are a blob store. So, as a credential wise, you need to have credentials to access the blob store. And the mechanism to get credentials into FDB uses the same FDB KMS mechanism and encryption key proxies to fetch it. So though it started with serving only encryption, we already have tagged volume credentials use case along with it. And the idea here is like, now you have a way to reach out to a non-FDB process. If you want to fetch information, you can use the same mechanism by adding your endpoint, leveraging the same, JSON request response, or maybe adding your own JSON request response, leveraging the REST client mechanism, leveraging the REST KMS connector, and the whole pipeline can be easily leveraged to add another use case. And that's what we did with the second one. Lastly, it implements in-memory caching. And the caching is kind of we feel it is kind of compose it in a way wherein the cache cells have time to live. So you, as in what, can set how long a cell is valid. And the variety of cell is different for the writes versus the reads. And the difference is because you want, when you rotate the keys, you want your newer data to be written with that key, but your old data is still valid to use the keys which have been rotated because they are still valid. So and this caching is always the one which kind of limits your commit or read latencies. If the data is already present, you need not to go out to KMS to get those information. And that was the primary reason for getting the caching built in. Sorry, this is a double slide. Sorry, I'll change it. This is the same slide repeated twice. It's not that important to repeat twice. The lifecycle management. Now, we did talk about how to get or how encryption key is being fetched into the system. This slide, what it represents is, what or how this information is being used. Now, in terms of scenario, what we will do is EKP is short form for encryption key proxy. Encryption key proxy or EKP would fetch the cipher from KMS, and then cipher has a configurable TTL. How the cipher is used is again, one of the thought that we put was, one of the standard is when you use an encryption key, you need to bound the data which is encrypted by that particular key. Now, that is an interesting challenge in FDB, because what we were doing is the encryption key could be used by commit proxy for writing the data on the T-logs. It could be used by, we only support Redwood, by Redwood for writing the node pages of the files, or it could be used by Blob to encrypt the files. It was very difficult to say, okay, how would I change the encryption key after 1 megabyte, 10 megabyte, 1 gigabyte, because you need to keep an accounting which is across multiple processes. We didn't want to do that. So the way we solve the problem is the cipher which is fetched from KMS is never used directly to write or encrypt any of the data. Every processes which is doing the actual encryption, they fetch this cipher, they derive a cipher out of it by applying a SHA-256 derivation and using a locally random number. And it's a non-deterministic for all protection use cases. And the encryption key that we get out of it is the one that is used to actually encrypt the data. Again, the cipher is time bounded. So you can control that, by the way, I want to just rotate the FDB internal cipher as much as I want. Your KMS cipher will still remain the same, but the actual encryption key FDB uses could be changed much faster than and this allows you to control and bound the creator with a single encryption key that has been used without having any accounting being built in. Now, the follow-up thing is, how would you represent this derivation? Because you need to have an in-memory representation of what this blob cipher key or the actual key is being done. So we came up with this in-memory structure which has enough information to first generate it for the writes. For the reads, because you're reading it from the disk, it has enough information to reconstruct the same key back, and which is being used for decryption. That key is not been stored anywhere. It's always generated on the fly, is in memory, and it disappears after memory. So you never persist that in encryption in FDB. Lastly, this was more of a, again, a learning that we did was, KMS is an external entity. We have a very good trust when we use FTP processes or FTP constructs. KMS is not an FTP construct, so we have zero trust what it could do. So what we do is we don't trust the value that we get from KMS. What FTP does is it generates what is called as a key check value. It's a 32-bit digest, and that digest is compared every single time it is being read from the KMS to say, by the way, it's possible that KMS bit rot, bit flip, or any other tampering could give you a different key. And now you'd be using different key, and that could be a ransomware attack by itself. So what we did is we had inbuilt key check value into the system, which compares whenever it fetches a value from KMS to say, by the way, do I trust it? If I don't trust it, I'll just fail it. And those failure messages are kind of evident. I should have done it, but I probably offline I'll also list the SEV 40s and SEV 30s, which are significant. If you find that in your prediction, these are the signs that something really wrong is happening. Now, following the journey, we did talk about how to encrypt, but one of the significant thing is once you write the data which is encrypted, how would you read it back? How would you know what to use to regenerate the key? So this was the on-disk structure that we added. Every buffer that is written encrypted is slapped with a plain text header on in front of it, and that is the payload that gets written. So we defined the encryption header, and again there was a lot of thought process to we put to how this header should be, and the reason being is given you always will be upgrading your system, you'll be adding new algorithm, you'll be changing it. So the way we designed this header is we tried to make it as configurable as possible. It is configurable in a way that your system can have, you can at least change the encryption algorithms on the fly. Say you are using algorithm A, then you use algorithm B, and the system can have multiple of data formats which it can read at any point. And the reason it can do that is because the header it supports evolution. It is also version, and you can change the versions and you can implement more and more types, and that is what header supports. What header is, and lastly, actually, one more thing it's worth mentioning. We did not use object serialization because we found that the object serializability, because of our configurable thing, was almost 3 times more expensive in terms of storage footprint than binary serialization. So we have used binary serialization. A header roughly is 46 bytes, the last I checked. If I use object serializable, it gets to 140 or 150 bytes now. So, that extra footprint that you spend by header, you can easily translate to the amount of storage space that you're wasting, because, this will be on a mutation level or a file level or a block level. So, we felt that saving those extra bytes was kind of, it will give us a benefit in the longer run. So we use the binary serialization for doing that. The header flags is the one that kind of makes the, header evolution easier. It supports information like what is the algorithm that you are using, whether it's authentic encryption, non-authentic encryption. It has a version definitely to evolve it. And as it is mentioned here, we started with a non-authentic encryption. Just a brief about non-authentic encryption is your encryption is written as a plain text, or header is written as a plain text. It is possible you can imagine an attack wherein reader just scans the disk, it can read header as a plain text bits, it starts, learning something, changing it, and it tampers your data. So when you read the data back, it's possible that, the tampering is done in a way wherein your decryption does not fail or crash. It still reads but gives you garbage value back. So the way to protect that is you can make your encryption authenticated, and that authenticated is the whole buffer has a digest. As a part of encryption, you can actually generate a digest. And if the tampering is happening, the encryption would fail by just looking at digest, saying, okay, plain text along with the encrypted text does not fit. I will kind of fail that operation by rather proceeding it. So the authenticated encryption mode, there are a couple of modes that are there. People should definitely look at their performance characteristics because they're expensive. We support HMAC, HMAC 256 and HMAC SHA. I guess probably 2 of them. I'm missing is HMAC SHA and CMAC. Yes, there are 2 that we support. Both of them are expensive. We found them to be, the penalty wise, one of them was like 150% more expensive if you just do a raw comparison in terms of authenticated versus non-authenticated. But again, based on the use cases, the sensitivity of data that has been stored, use your judgment, and then maybe that's one of the modes that is accepted to you. Another mode that we are, it's not upstream, but we actually kind of experimenting with that is AES GCM. So I did not go to the specific of AES CTR. Probably people are interested should look what CTR is, but that is one of the accepted industry standard or algorithms for encryption. Another one is AES GCM. And what GCM allows is it generates an authentication tag as a part of encryption itself. So it's an implicitly authenticated encryption mode. And the beauty of that is in the single encryption, when your payload is getting encrypted, it generates a tag as a part of it. So the penalty is actually minimal because you're not doing 2 different operations. And it is also, because of the Intel acceleration, it is cheaper in terms of performance penalty. So, but today in the, either it's the Snowflake upstream or the main, the supported mode is CTR with and without encryption. Now, how am I doing with time? Did I overrun already?
Yeah, a few more minutes. Maybe.
Thanks for saying that. So now going to the deep dive, and I'm trying to kind of wrap it up, or rather bring the point to home is, so this diagram kind of summarizes all the different things that we talked about. One thing that we do not talk about is like where the encryption is happening. And maybe this diagram is where we can actually see where encryption is happening. As I mentioned, the center of it is key proxy, and key proxy is a new process, just as a diamond, which has been, as a part of a legend. Now, we have three different storage tiers. One is commit proxy, which is eventually writing or generating the data into T logs, transaction logs, or write-ahead logs. Then we have storage engine. We only support Redwood for the encryption. We don't support SQLite. So the Redwood is the one that actually writes the data as files to the Redwood storage tier. Now, the encryption is done by the processes like commit proxy, Redwood, and the blob workers, which is the one which is running the backup. Now, the reason for the commit, the T-log is there was a choice wherein we could have done implement encryption on the T-log versus on the commit proxies. The reason we did not do it on a T-log is because, like if people who run production systems, they would have observed that T-log is always CPU bounded or mostly CPU bounded. So the T-log CPU is more expensive than commit proxy. Commit proxy is a stateless process. It's kind of, you can scale it easily. It's in the system. So what we did was we leveraged the commit proxy CPU to do the encryption. And the way we do that is and I should probably go here. So the way we do that is it is done on a permutation basis, not on a per transaction basis. We could have done on a per transaction basis, and maybe one day we'll do that. But the way we follow that is it is done on a permutation basis, and it is completely pertinent compliant. The way we implement it is we enhance the mutation rough structure. If anybody goes and look at the commit transaction, there is a mutation rough which defines what is the property of the ref. We extended that to add encrypted as a new type. And what it means is the encrypted has a, if you see mutation ref, it has a param1 and param2. It's a key and value. And the param1 is the serialized header. And the param2 is actually encrypted payload. And that is what is the encrypted mutation looks like in a system. This mutation directly gets written into a T-logs. So what is T-log storing is encrypted data. And where it is getting encrypted is in commit proxy. So, you're in your network, yes, there is a penalty because from commit proxy to T-log, your payload is slightly larger because of the header. But you're saving a CPU on the T-log, and T-log is just kind of serializing or in a sequential manner, just writing the blocks out of the T-log disk. One of the benefits of doing it a commit proxy is we could do an overlap, and we are given the FoundationDB actor framework wherein you can easily kind of parallelize the work. The way we do that is the expensive operation here is to get the encryption keys. Maybe it is a mess and you have to go all the way to the KMS. So we optimize and we do an encryption key lookup along with the resolution that Heming was talking that, the way FDB transaction works is there is a phase where in commit proxy gets the request, it is sent to the resolvers to see whether it is allowed to even commit those particular requests. And once the resolver says that all is good, then it generates a mutation to be written to T-log. All the T-logs will write it, happy life, and then the client gets acknowledged. So what we did was we saw a gap wherein the resolution phase anyway has to be a blocking phase on the commit. So we leveraged the resolution phase to fetch the encryption keys. And that is where we are saving the time in terms of the inline latencies being spent as a part of encryption. Yes, we are doing more CPU work. It could be wasted if the resolution says there is a conflict. But in most of the cases, that doesn't happen. Secondly, is that when you apply the metadata transaction, that is where the encryption is actually being done. So you fetch encryption key and then you do the encryption as a part of apply of your metadata, because that is where you have to encrypt the buffer. As I mentioned, the clear mutations are special because they can cross tenant boundaries. So the way we solve that is we split it across the transaction or tenant boundary. So one clear appears, n clears based on how many tenants you are actually trying to clear. So again, it's kind of pertinent compliant. We want to be very cognizant of the fact that how much penalty we are adding. So we were generous in adding the performance metrics and also adding the observability of how much expensive your encryption is. So there are the tracking in terms of how much of latency it is added on a batch level, on a per transaction or a per encryption operation level. So it is rolled up into a commit latency batch, wherein if you run with and without, you can see what is the penalty of your batch when it is getting encrypted, when it is not getting encrypted. And those are the metrics which are visible and could be used in production to compare how it is performing. Following the journey in the diagram, the second process that uses or needs to do encryption is Redwood. And Redwood is where, if we are, people are familiar with how it works, is your mutation lands into transaction logs from the storage servers, regularly peaks the mutation from transaction logs, and they will get, the storage server process will get it, it will supply that to the storage engine will then change the format in whatever acceptable format it has, and it will write the data to files or persistent storage. So the way Redwood organizes the data is as a B plus tree. So it has key prefix compression. So imagine the way it works is like it has a root, intermediate layer, and a leaf layer. Now, to follow, or the way we did the pertinent compliant encryption here is you can only have two ways wherein you can either have a node or intermediate node where you have data for a single tenant, or you have an intermediate node where the data or your key prefixes are actually containing multiple tenants. When it contains multiple tenants, we split them by only having the tenant ID portion of it and nothing else, because we keep on splitting the node. So in this graph, what I'm trying to kind of say is, if we go from bottom up, each leaf or each node page is the data for a single tenant. It doesn't contain data for multiple tenants because we kind of chunk it off. As you go at the level up, we follow the same philosophy, and if you have the data wherein you have multiple tenants, then you just kind of slice it up, and when you're writing it, you will write only the portion that belongs to a single tenant till you get to the point wherein the key prefixes are only tenant IDs and nothing much. So the whole tree is being sliced when it is being written out to make sure that the data from a single tenant is written in one chunk that is getting encrypted by its own encryption key. So again, it is done in a very pluggable way. There is a key provider which is generic, and to testing out this philosophy, there is already a XOR-based encoding scheme. All it does is kind of some fancy XOR operation to generate the encryption key, and that was to validate that the splitting is working fine. And then plus it has the real AES encoding being plugged in, which is being used in the production. So that is how we encrypt the encryption for the Redwood pages. Now, here, again, the same thing will be like this processes will reach out to the EKP when its local cache doesn't have that information, or the local cache information that the key has timed out. The philosophy is every single process that I'm talking about, the CPs or the Redwood, they will have their own local cache, because we want to minimize the inter-FDB inter-FDB RPCs or FDB to KMS RPCs as much as possible to make it as as fast as possible. The last encryption, and I'll really close it very soon, is the blob. And this is like, again, the blob worker writes in a much bigger file fashion. And at the end, what I've given is the file is written as an index block, and then each chunk is encrypted by its own. So you can control each chunk encryption, and you can even, it's possible to even rotate the encryption here. The process can actually rotate the encryption here. It is writing the chunk because it's all time based. But the uber point here is the encryption is at a file granularity level, and for Redwood it is at again a node page granularity level. For TLOG it is a mutation granularity level. So there are different levels in which encryption is done across multiple processes. This is the right path. It kind of says everything what I have been saying, but in a numbered way, wherein following the index, how the life cycle starts, what's the commit, then it tries to get encryption keys, and then so on and so forth. Same for the read path. Again, in a number fashion, it says how interaction would happen when anybody tries to read the data from FDB. Testing wise, everybody has talked about the simulation testing. It is great. It is actually great. It works fine. And we have, if testing would not be there, it would be very difficult to find the bugs. Just the permutation in terms of the determined simulation that we run is really I would say is phenomenal. It's kind of unbelievable how it can find bugs wherein there's no other way to find those kind of, or run so many probabilities of finding the bugs. So what we did was we actually extended by adding our simulated vault to have an end-to-end testing wherein the vault itself is simulated as a part of a simulation run, and we verify our communication protocol. Otherwise, that part will not be tested by simulation. So we have brought in this, the whole networking as a part of our simulation testing, and it is already been added to the code. We have done the benchmarking, and our, it's kind of very dependent on what the payload looks like. So I would encourage everyone to kind of, take a crack at it and see how to your payload, your transaction pattern, how the encryption works. But for us, the penalty was kind of a single low single digit number, what we observed with and without encryption. We have added benchmarking test suite, which kind of runs just a local benchmark, and it generates a payload of various sizes or fixed sizes, and you can see what I would say a vanilla encryption penalty would look like from benchmarking perspective. Again, this is for the future. What we want to do is maybe support a customer managed encryption key support. Periodic reking essentially is another standard is basically what you do is you have a guarantees that encryption key is used only for X time, and then after that even all the data gets scrubbed out. So for today, what we do is when we rotate the encryption key, we don't go and rewrite the data which has already been written. And what periodic reking would actually mean is, yes, you will be scrubbing data again and again. Some optimizations, but I think I can talk more about our future projects if people are interested. For the sake of time, I would end it here. Thank you so much first to Arvind and everyone in Adobe to organize this meet. It was fun to be a part of community, and happy to answer any questions.
I have a question, so
sure.
So you mentioned that right now we are not rewriting previous data, but wouldn't the perpetual wiggle sort of have that effect? And maybe the gap is just that you don't have a way to know for sure if the wiggle has happened for all the storage servers.
So perpetual wiggle was our story of not doing it. The only problem with the perpetual wiggle is it depends on how big your storage is and how often it runs. You can configure it to run, as faster to go, because perpetual wiggle is an expensive operation. You would be destroying every storage server and then recreating the storage server by writing the data back. Now, depending on how big your farm is, and another thing to consider is you will be churning your IOs. You will be actually using the IO cycles for doing that. Perpetual wiggle just for the periodic raking, I don't know. It's not. Doesn't seem like a very ideal solution. What you should be having is a tracking in terms of age. How what is the age of encryption key being used, and you can do a selective wiggle of the portion that is being aged out. What you do is when you wiggle it, you write the data that has been written half an hour ago or maybe 6 months.
You can only wiggle the data that needs to be
exactly.
wiggled.
It was not designed to do that. So we latched onto it, and we actually use that as a tool for maintaining the life cycle of a key.
So, thank you.
Please.
Go ahead.
No, go ahead.
Oh, I have a question on the KMS endpoint. So let's say the KMS is having an outage for a couple of hours. You said that the recovery would keep on doing an exponential backoff. Until what time have we tested that the cluster can be in a stage where it can recover?
So long, I would say. So actually, the way algorithm works is it has an upper bound of, it is not a purely exponential backoff, because it also has a problem if you are retrying after an hour or maybe more than an hour. So it is bounded by minutes and it is configurable. So what we wanted was the system should just kind of banging the wall, just keep trying forever. So for us, even ours, we have seen that the system kind of brings itself back rather than having us to force a cluster recovery. So it will be like, for us, it is a minute, and we bound the delay to a maximum minute, if I remember correctly, minute or 5 minutes. And in that fashion, it just keeps on retrying forever.
So while that retry is happening, are the other tenants' data accessible?
So if your keys are cached and they are valid, system will just work fine. Only the tenants or the operations for which the encryption keys are not available will fail. The only caveat here is the cluster recovery. Because when the recovery is happening, if you enter the system where a KMS is not available, then your cluster goes to another level. And we have seen that happening because your commit proxies die after a while. So that brings the sys cluster back to, or rather on its needs. Otherwise, the system will just work fine if the keys are cached.
But when the commit proxy dies, when the key is not rotated, then you're fine.
Yeah, there is an upper bound. I remember there is an IO timeout which we actually kind of played with. So there is an upper bound wherein system, if one commit is falling behind, then it kind of kills that commit to see, okay, I will recover that worker. But unfortunately, if the KM is unavailable, then your metadata is not even readable, and that will actually fail the recovery.
A few more questions, but I can wait till whoever wants to go next.
Jingu.
So for, you mentioned the commit proxy actually caches the keys. You also said during the resolution step, you also try to get the keys from KMS. Is that because some tenant keys was not cached locally?
Yes. So when we commit proxy, the first thing it will do is it will look up in its local cache. If that is missing, then it has to go to the KMS because it will first go to the EKP. If EKP has a cache hit, then we are lucky. The worst case, it has to go to KMS.
Makes sense. Thanks.
You also talked about the block cipher, having that in memory and then just using that. Is that, you don't get stored anywhere?
No.
Okay.
Because we don't have to store it. If you store it, then we will be acting like a vault. If FDB cannot act like a vault, or is not designed to act like a vault. I had one more hand on that. Yeah.
Sorry, I
Yeah.
just want to continue on one thing. And caching has to have all the keys, because if KMS is down, even if you have 99% cache, 1% is not caching in KMS, then everything will halt because the transaction will block. And then for that particular transaction, the commit proxy will.
So that
start
particular
timing.
transaction will block, but if you have a reads for some completely orthogonal tenant, that will succeed if it is cached.
But what about the other writes? So the commit proxy will start timing out for this particular
Exactly.
transaction, and it will.
That is what I was trying to say, that ultimately the cluster will actually be in an healthy state.
Okay.
It will get there, but how soon, it depends on what is the pattern of transactions.
And is that configurable somewhere? How many times commit proxy tries to retry the transaction and then goes into that state? Okay.
No, actually, here the commit proxy will not, I don't believe commit proxy retry transaction by itself. Like what commit proxy can do is, commit proxy can fail the transaction and then, the client has to retry.
Yeah.
Client always retry. What commit proxy will do is the key lookup, KMS key lookup is retryable. So the only thing retrying is a KMS key lookup, not the transaction itself.
Okay. Okay, and that is failed, and then the commit proxy will go into that state that,
Yes,
okay.
and then, once it dies and the recovery is triggered, recovery will fail because your KMS is down. Yes, sir.
A quick follow-up on, I think your comment you just made about we're not a vault. In the threat model where you have an unrecoverable backup, the ability to recover a backup depends on the KMS still being able to give you the keys from last week. It's not that there's any other further mechanism to log the key or store that in any other place.
Yes, that's correct.
On the perpetual wiggle question from earlier, right? It would be nice if you could, if there is a way to exhaustively find what are the generations of keys that are currently being used.
And this is, the second should actually do that.
Right. Okay.
So when we are implementing periodic reeking and, to expand to what I was discussing with Arvind, the ideal way would be at any given point of time, and post second and third, any given point of time, you should be able to say what are the active set of keys being used and along what the age of those keys are.
I mean, even if the system didn't automatically rekey, if that is available to us or to application, you could decide, oh, these are the N keys that are currently being used, and anything prior can be.
Yes, today actually that accounting has not been built in, and given it's distributed across multiple processes and multiple process rules, every process has to kind of say, by the way, this is what my known state is. And there has to be an aggregator to say, okay, this is the state at the FDB cluster level. And that is what is missing.
One more suggestion, in the diagram that you have in the previous, you may want to state that the encryption, that isn't really the encryption vault, it is actually the KMS proxy.
Yeah.
Which will then go to the encryption vault.
Yeah, actually, the reason I didn't want to distinguish it is because I don't know how people would implement it. It is very possible that, for the endpoint is also acting like a vault. A service can actually act as both. It could be a vault and also exposing the endpoint which FDB is connecting to. So you can disintegrate them, but it is possible to actually have them at the same time.
Right, I mean, and because none of the encryption key proxies plugins implement a public vault like HashiCorp or something, you kind
True.
of have to have a proxy.
True, but what I'm trying to say is like, even if it doesn't implement public vault, hypothetical example, I implement a service. And when FDB talks to my service itself is acting like a vault too.
Sure.
So that is the reason I don't want to, you can split them, but it is possible to be a single box. And this is like a black box. You can expand on this diagram in an organization acceptable way.
Makes sense.
Okay, I think Atta will be hanging out here for a few more minutes. So if you have questions, we could sync up offline. But I just want to thank you, Atta, for an excellent talk. Filled with lots of information. We're going to have follow-ups for you, but like, great talk.
Sure, thank you.
I just want to like give a big shout out to the team behind the organization, my Adobe team here. They were instrumental in putting all of this together and organizing it. So thank you guys. Again, I want to thank Himank and Atta for agreeing to come up here and give these amazing talks. I feel like I couldn't have picked two inaugural speakers, like you guys. So thank you for coming over and giving us this talk. So again, like I said, this is going to be a monthly series, so we will have one other meetup next month, and I promise there will be one or two speakers equally as interesting. Tall order, but we'll try to make that happen, and hope to see all of you folks there. And thank you.